Great, and you'll change this.
Yeah.
Okay, let's see, my name is Alan Needleman. I'm from Texas A&M University. I want to talk about dynamic crack growth in a plastically compressible solid. Reason for plastically compressible solids, interest in that, a lot of now foam materials, new materials, highly porous materials, and show the next slide. Okay, so there are a variety of solids that exhibit plastic volume changes, foam, some polymers, the porous metals. Plastic compressibility is often associated with hydrostatic stress-dependent flow. In fact, normality requires it. It can have a significant effect on the indentation response, I'll show that, and on local crack tip fields. The issue I'm going to want to look at is what is the effect of plastic compressibility, hydrostatic stress-dependent flow on dynamic crack growth. And all I have is a few preliminary results to show. This is really to advertise the fact that I think this merits much more attention than it's received to this point. There have been relatively few previous analyses of growing cracks in compressible elastic plastic solids. They've generally focused on quasi-static crack growth. I'm going to talk about dynamic crack growth. And they focused on near-tip fields. So the next slide. Okay, the constitutive relation is basically a rate-dependent Kirchhoff stress-based version of the foam constitutive relation of the Spandian Fleck. It's also specialization relation done for other contexts. It's plastic normality that some work with Julia Greer and Shelby Hutchins on carbon nanotube foam type solids. So, standard elastic plastic, small elastic strains. The main point is there's one additional parameter, says the plastic compressibility. This is the DF is the Spandy Fleck. That's their parameter. There's also an effective Poisson's ratio. So either alpha DF, or new plastic, all characterize, and one additional thing to characterize the compressibility. Very simple relationship, power law, rate hardening, power law, hardening. If alpha is 1/3, this is a half, that's compressibility. Alpha is 1/3, this is, let's see, the square root, the 3 on the square root of alpha is 1/3, this is 0. So it's different ranges of parameters. Next slide. Okay, this is to illustrate the effect on indentation. Here, just hydrostatic stress contours underneath an indenter. Okay, the negative stress goes down to 2.5 times the flow strength. These are normalized. Here, it only goes down to less than 1 time. Again, you're compressing, you reduce the hydrostatic stress. Big effect. Next slide. Crack tip fields. These are stationary crack tip fields, small scale yielding, finite deformation notch. This is an incompressible solid. This is a plastically compressible solid. See how the crack tip fields change significantly. Next slide. Okay, so this is what I'm going to look at. A center crack panel, but not small scale yielding. So the whole panel. Plane strain, finite deformation, symmetry conditions, so we're going to look at 1/4 of the panel, put on basically a constant velocity after a certain rise time. So, and this is the dynamic principle of virtual work. Going to have a cohesive relation in front of the crack, nonlinear springs, and so crack growth is just restricted to be straight ahead. Next slide. Okay, here's the cohesive relation, just little springs in front. The stress goes down to essentially 0. This is called the Uber relation, universal binding energy relation from Ferranti and Smith. Here are some material properties. Why these material properties? Because I had some results from years ago in the incompressible case, so there was something to compare to. A very low cohesive strength, and That's the cohesive let scale. Next slide. Okay, the finite element, going to use linear displacement across triangle quadrilaterals, explicit time integration, lumped mass, very easy calculation. You can do it on a little laptop, and a rate constitutive update. Next slide. Okay, here's just a simple mesh for the 1/4 being analyzed. The crack tip somewhere in here. Crack growth happens in this fine mesh region. Okay, next slide. Okay, so here's crack growth rate versus time. Okay, now we're going to look at 4 values of alpha, or this effective Poisson ratio, or the Despondy-Fleck factor. If this is 1/3, 0.33, this is nearly a half. This is 0.067. 0.31 goes down to 0.45, 0.43, 0.29. This goes down, the Poisson ratio goes down to 0.48. The Despondy-Fleck factor changes by more than an order of magnitude. Okay, what happens? Crack growth rate, so we can look at crack growth, delta A, delta T, versus time. This is for an incompressible, plastically incompressible solid, slightly compressible solid. The speed changes enormously, but nothing qualitatively changed. Go down just to 0.30, which means Poisson ratio of 0.43, crack growth rate becomes essentially, loses its dynamic character. And if you go down to 0.29, the crack just sits there and blunts and blunts and blunts. Next slide. Okay, so we can do JR curves. This is the dynamic J. You know, J is the path-independent integral. You probably know about the dynamic J. What you do, it's really clever cheating. What you do is whatever's left over, you just stick it as an area integral, and you call that path-independent. So yes, it's whatever's, you know, it's like energy balancing when you have friction. Whatever's dissipated, you just add it in. So, but if you do that, and now you can calculate JR curves, J resistance curve. So for an incompressible solid, basically it's steady, constant J crack growth. It's almost elastic. If it were the Griffith energy is 1, this is 1.1, something like that. You add a little bit of compressibility, you increase the crack growth resistance, a little more, and it goes up enormously. That was a little bit of a surprise. Okay, next slide. Okay, these are plastic zones. So this is incompressible. And what happens is you get large-scale plasticity. Remember, in the constitutive relation, a little bit of hydrostatic stress does 2 things. It lowers the hydrostatic stress dependent, lowers the hydrostatic stress, which is big near the crack tip, makes that lower, but also it increases the flow strength because it now adds another term to the flow strength. So you get much larger plastic zone sizes, and as you decrease alpha, you get enormously more plasticity. So spreading out the plasticity, lowering the hydrostatic stress, enormously affects crack growth. Next slide. Okay, these are the near tip, just not mesos, but the work conjugate effect of stress. This is again for incompressible. This is compressible. This is more compressible. Fine, so here what you're doing is you're actually increasing the effective stress, but lowering the normal stress, which drives the decohesion. So you get more plasticity, more dissipation. By the way, I'm sure it's well known to at least most of you that, you know, if you look at in any ductile material, or actually almost any material, you look at the work of fracture, of actually making new free surface. It's a very small percentage of the total work that's dissipated in fracture. What really contributes to fracture toughness is the large-scale plasticity, large-scale dissipation. And what this is doing is increasing the large-scale dissipation. So anything that does that has an enormous effect on toughness. Next slide. Okay, this is the near-tip hydrostatic stress. And incompressible, slightly compressible, slightly more compressible. And you see the local hydrostatic stress, which contributes to the normal stress, keeps going down. Next slide. Okay, the concluding remarks. Okay, I didn't have much to say. So, in these circumstances at least, plastic compressibility lowers the near-tip stress level. The reduced near-tip stress level, normal stress level, significantly retards crack growth. With increasing plastic compressibility, the opening stress just falls below the cohesive strength. It goes back to work that Vigo and John Hutchinson did for incompressible materials years ago. And that can then preclude crack growth, at least according in these calculations. Relatively small changes in plastic compressibility have a large effect on the computed crack growth speed and crack growth resistance. And I think more detailed analyses of dynamic crack growth in plastically compressive solids are warranted. And one can think of using, you can make now these much more porous, compressible solids. One can think of using them in layered structures to enhance crack growth resistance. How that affects things remains to be done, but I think there's a lot of interesting open questions here for future work. Thanks for your attention.